Skeletal system is going to include bones of the skeleton, cartilage, joints, ligaments, connective tissue. The connective tissue is going to help to stabilize or to connect bones together. Now, there are several functions of the skeletal system. The first would be support. This provides structural support for the entire body. The bones provide attachments for soft tissues and organs. The second function is the storage of minerals and lipids. Mineral reserves for calcium and phosphorus ions are held in calcium salts in the bone. The yellow bone marrow actually will store lipids for energy reserves. Third function is blood cell production. All of your blood cells, whether they're white blood cells, red blood cells, or platelets, are all going to be produced in the red bone marrow. Protection. You have a lot of soft tissue organs, such as your heart, lungs, and these are going to be surrounded by skeletal structures. Another important one is the brain, which is enclosed by the skull. Fifth function would be leverage. What happens is muscles will pull on bones, and that allows for movement. So bones will function as levers. They'll change size and direction of force that's generated by the skeletal muscle, will allow for actual body movements. So let's look at bone tissue, or also called osseous tissue. Supporting connective tissue that contains cells in a matrix. That is what bone tissue is. The cells are called osteocytes, and the matrix is primarily composed up of calcium salts in the form of calcium phosphate. This actually accounts for almost about 2/3 the weight of bone. Extracellular protein fibers will account for about 1/3 the bone weight, and this comes primarily from the collagen fibers that are present in bone tissue. There are different types of bones. We have long bones. They are longer than they are wider. Short bones. They're about as wide as they are long. Flat bones. They're thin and relatively broad. And then irregular bones. These are complex shapes that don't fit another category, so they're just thrown into this category of irregularly shaped. And here you can see a picture of each of those 4 different types of bones. So let's look at some features of long bones. The diaphysis, this is the central shaft. It surrounds a marrow cavity or medullary cavity, and in that center, it is filled with bone marrow. The epiphysis, these are the expanded portions at each end. They're covered with the articular cartilage, and they articulate with the adjacent bone at a joint with another bone. And here we can look at the structure of a long bone. Here you can see the diaphysis. This is the long part of the bone. And what you have in the center here is the medullary canal. This is oftentimes filled with marrow. And then the ends are called the epiphysis. And you have one at this end and one at this end. Long bones will be covered with an outer surface covering called a periosteum. And the periosteum will contain an inner cellular layer and an outer fibrous layer. The outer fibrous layer is going to isolate bone from surrounding tissues. We'll also form attachments with fibers of tendons and ligaments. The inner surfaces and the spongy bone of the marrow cavity are covered by endosteum, and they will function during bone growth and repair. The different types of bone tissue that we find in long bones. You have compact bone or dense bone. This is relatively solid, and it forms the wall of the diaphysis. Spongy bone or calcaneous bone. This is the interlacing network of bony rods separated by spaces. This fills the epiphysis and it lines the marrow cavity. And if we go back to this picture here, you can see this would actually be compact bone right here. And then this would be spongy bone, sort of has that sponge appearance. Believe it or not, out of the two, the spongy bone is stronger. Looking at the microscopic features of bone, when you guys looked at bone tissue back in an earlier chapter here, we saw this picture. And what you're mostly seeing here is calcium phosphate. These little black slits of the lacuna, these are the pockets in which we'll find the osteocytes, which are the bone cells. Caniculi, These are small channels. They contain cytoplasmic extensions of the osteocytes, and they radiate through the matrix. They connect the lacuna to blood vessels for nutrient and waste exchange. So these little caniculi, these are little channels that will allow the blood vessels to sort of feed these individual osteocytes. Looking at the basic histology of compact bone, the basic functional unit is called an osteon, or a Haversian system. Osteocytes arranged in concentric layers called lamella. The layers surround a central canal or Haversian canal. The central canals run parallel to the surface of the bone and contain blood vessels. You'll also have perforating canals. Some books will also call these Volkmann canals, but I think your textbook just calls them perforating canals. And this is the link. This is to link blood vessels of the central canal with blood vessels of the periosteum and marrow cavity. And here we can see an osteon, okay? And you can see the blood vessels going through, okay? And this would be one of those perforating canals that sort of runs perpendicular that'll allow us to connect one osteon to another as far as the blood vessel supply is concerned. So looking at compact bone, covers all bone surfaces except the inside joint capsules. The articular cartilage protects opposing bone surfaces here. Parallel arrangements of osteons resist stress in specific direction. This will actually withstand forces applied on either end of the long bone, which is typically where a lot of force will be applied. It cannot tolerate moderate stress applied to the side of the shaft. And oftentimes that can actually be a site for breaks. You know, if you hit the side of a bone, especially in that shaft, you'll really cause a break pretty easily. Spongy bone will not have any osteons as far as their structure is concerned. The lamella will form rods or plates called trabeculae. There is no central canal. It still contains osteocytes, lacuna, and caniculae. The spongy bone will also contain red bone marrow, and this is found in spaces between the trabeculae. Some functional features of spongy bone. They're found in locations not heavily stressed, locations with stress is arriving from many different directions, because spongy bone will actually give you protection in multiple directions. Example, the epiphyseus of the long bones, where stresses are transferred across the joints, is where we'll find spongy bone. Spongy bone is also much lighter than compact bone. It reduces the weight of the skeleton. It's easier for muscles to move bones. Now, there are several different types of bone cells. We have osteoblasts. These produce new bone through the process called ossification. Osteoblasts are surrounded by bony matrix, change into osteocytes. So they will eventually, osteoblasts will convert into osteocytes once they form the matrix. Osteocytes, these are the most abundant cells in bone. They mature cells that maintain the bone structure by recycling calcium salts. And then finally, osteoclasts, these secrete acids and enzymes that will dissolve the matrix of bone. The process releases minerals through reabsorption. So how do we form bone? Embryonic development of bone begins at week 6 as a cartilage formation. It's replaced with bone in a process called ossification. There are 2 types of bone formation: intramembranous ossification and endochondral ossification. Calcification occurs during ossification. This can also occur in other tissues besides bone. For example, cardiac muscle tissue can calcify over. During intramembranous ossification, this occurs during fetal development starting around week 6. Bone develops within sheets of fibrous connective tissue. It begins in an ossification center. Osteoblasts will differentiate from connective tissue stem cells. Bone matrix formation extends outward. Blood vessels will infiltrate the bone. The blood vessels will grow into an area and are trapped within the developing bone. They become deposit areas of the bone marrow. Primarily, cancellous bone formation. Flat bones of the skull, mandible, are actually formed in this manner of intramembranous ossification. Endochondral ossification, on the other hand, this is the process of formation for most bones of the skeleton. It begins with hyaline cartilage models. The cartilage is replaced by true bone. And here we can see in the first stage, chondrocytes at the center of the growing cartilage model will enlarge and then die as the matrix calcifies. The newly derived osteoblast will then cover the shaft of the cartilage in a thin layer of bone. What then starts to happen is blood vessels will penetrate the cartilage. New osteoblasts form a primary ossification center at the center of the cartilage model. The bone of the shaft thickens, and the cartilage near each epiphysis is replaced by shafts of the bone, and then finally, the fifth stage, blood vessels will invade the epiphysis, and the osteoblast will form secondary centers of ossification. There's a structure called the epiphyseal line. At puberty, bone growth accelerates due to increased sex hormone production. Osteoblasts will produce bone faster than the epiphyseal cartilage can grow and expand. The epiphyseal cartilages get narrower until they disappear, and this is called the epiphyseal closure. X-rays of adult bones show former location of the epiphyseal cartilage, referred to as the epiphyseal line. And if you actually took a image of an X-ray, you can actually tell whether the epiphyseal line has closed or if it's still open. If the epiphyseal line closes, there is no more growth of the long bones. Okay, so looking at appositional growth, this is growth in the diameter of bones. This will occur along with growth in length. In the process of growing in diameter, the thickness of bones, this is referred to as appositional growth. The periosteum cells will develop into osteoblasts, and they will produce more matrix on the outer surface of the bone. The osteoclasts will erode the inner surface, and the marrow cavity enlarges as a result. And here you can see that with the appositional bone growth, how it starts off thin, but it eventually thickens up and you build up that density, especially in adult bones. Now, the timing of the epiphyseal closure, this can vary from bone to bone. Digits close early. Arm, leg, and pelvis bones will close later. This will vary from person to person. Different timing in males versus females, mostly due to differences in sex hormones and later closure within males. The requirements for bone growth: mineral supply, you'll have calcium salts, which are calcium and phosphate. This is absorbed from the mother's bloodstream during prenatal development. And then vitamin D3 plays a role in calcium metabolism. Liver and kidney process into calcitriol, which will stimulate calcium and phosphate absorption. It's manufactured by the epidermal cells exposed to UV radiation. Also obtained from dietary supplements and dairy products. Deficiency in vitamin D3 leads to softening of bones, a condition called osteomalacia in adults and rickets in children. We really don't see this in the United States anymore, as this is something that's picked up by pediatricians, and most children are meeting the minimum requirements for vitamins. Vitamin A and vitamin C provide support for osteoblast. Various hormones, growth hormone, thyroid hormone, sex hormones, and then calcium balancing hormones, PTH and calcitonin, can all aid in bone growth. Now, bone remodeling, this is a process that recycles and renews organic and mineral components of bone matrix. Osteocytes will maintain matrix, continually removing and replacing calcium salts. Osteoclasts will continually remove the matrix. Osteoblasts will continually build up the matrix. And its normally activity is then balanced. You don't want an imbalance in the remodeling process, meaning you don't want to break down more bone than you're replacing, and you don't want to replace more bone than you're breaking down. The turnover of minerals gives bone the ability to adapt to new stresses. Heavily stressed bones are thicker and stronger. Regular exercise is important in maintaining bone structure. Bones receiving lower than normal stress are thinner and more brittle. Inactivity, such as using crutches, results in loss of bone mass. Now, the skeleton as a calcium reserve. Calcium is the most abundant mineral in the body. 99% of calcium is deposited in the skeleton. The calcium shifts between blood and bone. Essential minerals for many physiological purposes, such as neuron and muscle cell function, are going to be using calcium. And if the body needs that calcium for these particular functions, it will actually pull it from bone. Calcium reserves are very closely regulated, and they require small changes in calcium ion concentrations, which could affect cellular functions. Larger changes can cause convulsions or death. Calcium balance in bone and blood is regulated by two hormones: parathyroid hormone, which will raise blood calcium levels, and calcitonin, which will lower blood calcium levels. So it's a balance between those two. Fractures and breaks. A fracture is a crack or a break in a bone. Two broad categories on the external appearance. Is a closed or simple fracture. This is completely internal, no breaks on the skin, and can be only seen on x-rays. Open or compound fractures, these project through the skin, more dangerous due to the risk of infections. Fractures also named by nature or location of the break. Okay, so now let's look at the different divisions of the skeleton. The skeletal system consists of 206 bones. There are two divisions, the axial and appendicular skeleton. The axial skeleton will consist of the skull, rib cage, and spinal column. The appendicular skeleton will consist of the appendages, the pectoral and pelvic girdles. Pectoral is your shoulder joint, pelvic girdle is your hip joint, which are attached to the arms and legs respectively. And here you can see the breakdown of the axial skeleton bones versus the breakdown of the appendicular skeleton bones. There's 80 axial skeleton, there's 126 appendicular. Okay, and this is where I'm going to end recording number 1.